Hey class, today we're going to start the last section in chapter 2, which is actually section 2.2 titled Mixtures. So far we've talked about properties, chemical and physical changes. We got introduced to elements and compounds, and now we're going to introduce ourselves to mixtures. Before we give the definition of a mixture, let's go over the two types of matter that we've already talked about so far, and that is the element and compound. An element is defined as the simplest form of matter that has a unique set of properties. Remember, we cannot break down an element further. A compound is a substance that contains two or more elements, and remember these are chemically combined, and they are chemically combined in a fixed proportion, which means they're going to combine the same way each time. For example, on H2O, there's always going to be two more hydrogen than there are oxygen. These two parts of matter we called substances, because substances have a uniform and definite composition. The new type of matter is a mixture. A mixture is not a substance. The other key word about this definition is it is a physical blend. So nothing is chemically bonded. This is just a physical blend of two or more components mixed together. So as a little introduction, it starts off with showing us a picture of a salad. A salad bar provides a wide range of items such as lettuce, tomatoes, cheese, green peppers, croutons, cucumbers, you name it, there's a lot that can be put on a salad bar. And customers are going to go up to that salad bar and choose which items they want to put on their salad, but also how much of each item. So one thing to note about a salad is that there are different types and there are different amounts of each component, and that's the key thing. There are different types and amounts. There's no longer a uniform composition or a fixed composition. The composition can change. So one thing to note is that actually most samples of matter that we look at in the world are actually considered mixtures. Some mixtures are really easy to recognize, like salad or chicken noodle soup. We can see the chicken and we can see the noodles and we can see the broth. And then others are a lot harder to recognize. And so the ones that are really hard to recognize are usually solutions or air. Air is one that's really hard to recognize. It is actually a mixture of gases. Our air is a mixture of nitrogen gas, oxygen gas, carbon dioxide, carbon monoxide. There's a lot of different gases in the air. But how do we know that air is actually a mixture? One way that we know that air is a mixture is because air can actually be drier or it could be more humid outside, and that's because one of the components of air, which is water vapor, can vary. If there's not a lot of water vapor in the air, we get a drier air. If there is more water vapor as mixed as part of the air, that's when we see it get more humid out. So how can we actually classify mixtures? What we do is we classify mixtures based on the distribution, and when I say distribution, is going to be how are they spread out. So how are the components spread out? And there are two types of mixtures that we're going to talk about today. The first one is heterogeneous mixtures, and then the second one is homogeneous mixtures. You might hear other teachers call it homogeneous mixtures. Either way you say it is perfectly fine. Let's look at heterogeneous mixtures first, or heterogeneous mixtures first. This is a mixture in which the composition is not uniform throughout. So that means when we look at this composition, we can see the different parts of it. Hetero, this little prefix means different. So if you're looking at chicken noodle soup, you can see the different parts of chicken noodle soup. If you're looking at sand really closely, you can see the different parts of the sand, the quartz from the dirt, from the little rocks. Muddy water, you can tell the difference between water and the mud. Oil and water. It separates. You can tell the difference between oil and water when you try to mix them together. Homogeneous or homogeneous mixtures, on the other hand, is where the composition actually looks uniform throughout. So 2 examples of this. This is olive oil. When I look at this, it looks like it is only made up of one substance. You don't realize that this is a mixture of things. Same thing with vinegar. Vinegar is a mixture of actually acetic acid and water. And it's hard to tell that because it mixes or it's dissolved in the water. Gasoline, sugar water, Kool-Aid are all other examples of homogeneous mixtures where the composition looks uniform throughout. Another name for a homogeneous solution is actually called a homogeneous mixture is called a solution. So if I go back a slide and I said sugar water was an example, salt water is also an example. And you might have heard someone say salt water solution if they were asking you to gargle your mouth because you had a mouth sore. Again, because another name for a homogeneous mixture is solution. Now, a solution or homogeneous mixture can be made up of liquids like we've seen on the previous slide, like salt water, sugar water, Kool-Aid. It can also be gases like air. We said air was a mixture that was really hard to tell that it was a mixture, and that's because it's a homogeneous mixture. And still there are still homogeneous mixtures that are solids that we call solutions, and these are like things like stainless steel. Stainless steel is actually a mixture of iron, chromium, and nickel all together. Brass is another one, or even bronze is also a mixture of metals as well that are melted together. Now with this idea of mixtures, there's this term called a phase. A phase is just any part of the sample that is said to have a uniform composition or properties. Again, any part, keyword there, any part of the sample. So if we're looking at a homogeneous mixture, this right here is said to be a uniform composition because it looks the same. So right here, this homogeneous mixture only has one single phase. Even here, if we look at this homogeneous mixture, this all looks the same, so this has one single phase. But if we look over here in this tube, I can see this part of the sample, and I can see this part of the sample. So there are two parts that look uniform with one another. And so this has two phases, and anything that has two or more phases is heterogeneous. A salad, say you had a salad made up of lettuce, onion, tomato, and croutons, that has 4 phases. So how do I know if it's a substance, or how do I know if it's a mixture? Again, let's redefine. Remember, a substance is an element and compound. So deciding whether or not a sample of matter is a substance or a mixture, we cannot solely base it on appearance because that can be difficult. Like we said, some mixtures are hard to tell that they're mixtures. All homogeneous mixtures and any substance will appear to contain only one type of matter because it has that uniform look to it. So, how can we actually do it? The one thing we have to look at, again, it all comes down to composition. Just like it did with chemical and physical changes, that's what it's going to come down to, knowing if something is an element, a compound, or a mixture. If the composition of the material is fixed, which means the composition does not change, so remember, fixed is does not change, we are going to consider that a substance. However, if the composition can vary, which means it changes, we call that a mixture. For example, a salad can vary based on if it has, lettuce, tomato, onion. Air can vary based on whether it has more or less water vapor in it. Chicken noodle soup can vary depending on if it has more or less brass in it. More or less broth in it. And so one thing that you can ask yourself in whether or not something is a mixture or not is, can you have more than one version of this? Milk is another good example. This is actually a homogeneous mixture. You can actually buy whole milk, low-fat milk, no-fat milk, light cream, heavy cream. All of this is a type of milk, and you might infer that these are actually mixtures because they contain different amounts of fat. 2% versus 1% versus whole milk have different amounts of fat in it. And that's how we know that milk is a mixture. Specifically, it's a colloid. Gas, we can also recognize that gas is a mixture, because when you look at gas, you can say, oh, if you go up to a gas pump, there are different types or different blends. Each of these blends have different octane readings, and they cost different amounts per gallon because of how much ethanol is in them. So gas is also considered a mixture. Well, gasoline. So this little chart here, I do highly recommend that you guys fill it out in your notes, because it's going to give a little chart to figure out if something is a mixture, element, or compound. The first question you're going to ask yourself is the composition fixed? Means, does it have an element symbol, or does it have a chemical formula? And if the answer is yes, then you're going to ask yourself, can it be broken down chemically? And if the answer is no, it cannot be broken down and it's an element, the answer is yes, it is a compound. If you answer no, that the composition is not fixed, which means the composition can change, then you're going to ask yourself, does it appear uniform throughout? If you say yes, again, that's homogeneous, which we also call a solution. If you say no, that is going to be a heterogeneous mixture, which means you can see distinct phases. Remember, this is 2 or more phases. In the last part of this lesson, we're going to talk about mixtures and how do we separate them. And you'll actually be doing a lab on this. It starts off with saying, if you have a salad containing an ingredient that you don't like, such as croutons, I do not like croutons, I can simply remove them with a fork. Some mixtures are easy to separate, like the salad's croutons, or some are not easy to separate. So how can we actually separate them? Again, because they are physically combined, we cannot utilize different, or I should restart. Because they are physically combined, we are going to use physical properties to separate them. Remember, physical properties are things that we can observe and measure, and it doesn't change what the object is. So that's like mass, color, size, boiling point, densities. Here, oil and water have different densities, so you should notice in our lab that one floated on top of the other. So you can actually just pour off or decant that top layer. They also have different freezing points, so you can actually cool the sample until one of them turns to solid and then pour the liquid off. Another process is filtration. Filtration actually separates a solid from a liquid if you had a heterogeneous mixture. Filtration is based on particle size. So again, how big are those particles? Anything that is a solid or a large particle is going to stay behind on a filter, and we're going to see this in lab. And anything that is a liquid or small particles are going to pass through that filter. It's the same thing as if you were trying to make coffee. Here we have a coffee pot, and here we have a coffee filter. It's going to separate the coffee grinds from the coffee being brewed. Again, the liquid's going to be able to pass through this filter paper, but any of those solid coffee grinds are going to stay behind and not pass through. The other type of technique for mixtures that is talked about in chemistry is distillation. Distillation is when a liquid is boiled to produce a vapor. Remember, a vapor is a gas. And then that gas is condensed into a solid. So when we say condensed, it means we're just changing that gas that we created back into a liquid. And distillation is based on difference in boiling points. For example, something is going to turn into a gas before the other substance we're trying to separate out. The biggest way we use distillation is in the form of tap water. Tap water is actually a homogeneous mixture, and it is actually water with a bunch of other things dissolved in that water. We got chloride ions in the water and other things that are just typically in tap water. And so we would want to separate out pure water from the other components in it. And we use that difference in boiling point. So here is our little setup. Here we have our tap water mixture in a flask, and we're heating it up. So as water in the distillation flask is heated, what's going to happen is that since that water vapor has a lower boiling point than everything else, that water vapor is actually going to turn into steam or a gas. So again, here we get steam. And then it's going to pass through this tube, which we call a condenser. This condenser is actually surrounded by cold water, and that's going to cool off that gas and have it lose enough energy where that gas in this tube actually, again, condenses and turns back into a liquid. So down here, we end up getting pure distilled water. So again, the liquid water collected in the second flask. Everything else is going to be left behind. So again, water is going to end up over here and everything else will be left behind, and that's because of the difference in boiling points. Again, those components' boiling points are much higher than the boiling point of water. And that's the end of today's lesson. If you have any questions, please make sure that you ask, and I hope you guys have a great day.